lecture series on differential equations for undergraduate students. Today's topic is three-dimensional Laplace equation. We are learning about some important partial differential equations which are very important in application, engineering and physics. In that series, today we will learn about three-dimensional Laplace equation. You have seen in example that second order linear equation del 2 u over del x 2 plus del 2 u over del y 2 plus del 2 u over del z 2 is equal to 0. This is three-dimensional Laplace equation. It has been called in the three dimensions since we are having three coordinates x, y and z, and u is a function of x, y and z only. We are not having it is independent of t. This left hand side of this equation is called the Laplacian. This is very important equation in physics as well as in engineering applications. It is arising mainly in gravitation, electrostatic, steady state heat flow and steady state fluid flow, all the studies of these things it is coming. The solution, that is how to find out the solution of this equation, theory of solution of this Laplace equation is called the potential theory. So, we are also calling it potential theory, that is understanding the solution of three dimensional Laplace equation. The solution, if it is its partial derivatives are continuous, that is solutions which have continuous partial derivatives, they are called harmonic function. Let us come to the one application, that is gravitational potential. We had learned in physics that gravitational potential u at x, y, z resulting from a single mass located at the point x naught, y naught, z naught can be given as a function u x, y, z as c by r, where c is a constant and r is the distance between the point where this mass is located x naught, y naught, z naught and the point at which we are calculating this potential x, y, z. So, we do get is that this we could write the distance as c upon square root of x minus x naught square plus z minus z naught square plus y minus y naught whole square. If we just apply this del 2 u over del x and del 2 u over del y 2 plus del 2 u over del z 2, we find it out that Laplacian of this is 0, that is it is satisfying this Laplace equation. Now, if similarly we define the masses distributed in the region T in the space with density rho x naught, y naught, z naught, then its potential u at the point x, y, z not occupied by the mass is given as k times integral on the region T rho of x naught, y naught, z naught upon r dx naught, dy naught, dz naught. Again this will satisfy our Laplace equation, since this integral is with respect to x naught, y naught, z naught and rho is not depending upon the point x, y and z, and again 1 upon r would has the Laplacian as 0. So, we do have that this will also satisfy this one. So, from here let us move to the theory of solving this Laplace equation. For solving of the Laplace equation, practically it is resulting in the boundary value problems. We define the boundary values problem because we are having is that the region is three dimensional. So, it is a three dimensional one. So, let us see here is the example of a sphere. You could say any three dimensional mass in which we are interested, the region is this three dimensional solid T, and we do have it has been covered by a surface, that is we are calling S. So, we define the three kind of boundary value problems. First boundary value problem or Dirichlet problem that we are calling, in which the boundary condition is given on the surface, or that is the boundary of the region, that is u is given on S, that is boundary. Second kind of boundary value problem, or that we are calling Newman problem, in which the boundary condition for the rather than for given for the u, we are being given that is normal derivative of u is being defined on the or is being prescribed on the boundary S. And in the third kind of boundary value problems are called the mixed problems, in which in a portion of boundary S u is being prescribed and the rest of the portion of S the normal derivative u in is prescribed. We had seen that in 2 dimensional problems also, 2 dimensional Laplace differential equation also, we had seen that their reason was our a planar reason. Here we are having the reason is 3 dimensional solid reason. There we used to have the reason was a planar reason and the boundary was a curve. Here boundary would be the surface, and in the similar manner we have defined Dirichlet problem, normal this Newman problem and the mix problem. So, let us we would start with the Dirichlet problem first, that is when the boundary condition is or the u is defined at the boundary S, surface S. For solving it, we do require is that we first actually make the change of coordinates or change of variables. The coordinates x, y, z, they are the variables. So, we change the variables in such a manner that the region S, that is the surface S, becomes more simplified. So, in that one first we see if my surface is having cylindrical symmetry. So, the solution of boundary value problem, we first see if the surface is having cylindrical symmetry, that says is, suppose let us say for example, my surface is that my region is this cylinder and surface is, that is for boundary condition we are defining the surface of this cylinder S. Then we would change my Laplace equation into the cylindrical coordinates. What are the cylindrical coordinates? They are being defined, that is we are transforming x, y and z, the Cartesian coordinates, into the coordinates r, theta and z, where the relationship between them is x is r cos theta, y is r sin theta and z is equal to z. We will learn a little bit later, that is how they have been obtained. Similarly, suppose my problem says is that the boundary is spherical symmetric, that is we are having is the reason is some ball and the surface is its sphere. So, let us say this is the reason is this unit ball and then the surface is of this one. So, we do have that surface is boundary is sphere. Then we would like to change my Laplace equation from this Cartesian coordinates, that is x, y, z, to the spherical coordinates. What are the spherical coordinates? They are being given in the terms of r theta and phi, and the relationship between x, y, z and r theta phi are being defined in this relation, that is x is r cos theta sin phi, y as r sin theta sin phi and z as r cos phi. Let us see first, that is what these coordinates are, and that is what are these cylindrical coordinates, what are these spherical coordinates, and how we are transforming our Laplace equation into these new variables. So, let us see one by one Laplace equation in cylindrical coordinates. So, this is our given Laplace equation, del 2 u over del x 2 plus del 2 u over del y 2 plus del 2 u over del z 2 is equal to 0, which is defined in the variables x, y and z. Now, we want to define them in the terms of new variables which we are calling cylindrical coordinates. Let us see what we mean by cylindrical coordinates. As I said is that if my surface is having cylindrical symmetry, to remember that is we are having is that cylinder is circular on the base points, or you say is that any cross section is circle, while you do have that height is straight line. So, that is how we are defining, that is in this 3 dimensional space any point, as in the Cartesian coordinates we are defining this point as x, y, z. Now, I would represent this point with 3 coordinates now r, theta and z. Z is same thing, is that is if I take what is the distance along the z axis of this point from the x, y plane. So, we do have this simple Cartesian plane. From the x, y plane, whatever the distance from this x, y plane to this point z we are having, that is if I drop a perpendicular from this point to the x, y plane, this distance, this height would be called z. So, this is what cylinder, but what we are having is in x, y plane when we talk about, that is this one would be a circle. So, here if you do remember, that is in the 2 dimensional one we are defining polar coordinates. So, we define here, that is because of circle we are defining the polar coordinates, that is the point which is coming on the x, y plane. For that the distance from the origin r and the angle it is making with the x axis, that is theta. So, what we now this point we are defining is, this point is being transported to the xy plane, and in xy plane we are using the coordinate system r and theta, and this is z. So, this is what we are having is cylindrical coordinates. From the polar one we do know, if I am denoting this r is the distance from the origin to this point, if this point in xy plane is x into y, then we do know that x is nothing but r cos theta and y is nothing but r sin theta. Z is same as z. Since we want to change my Laplace equation into this new variables r theta and z, that says is these derivatives of the function, that is the function u x y z, now we would write it as u r theta z. So, when we are changing it, so this derivative with respect to x, y and z, that we have to change the derivative with respect to r, y, r theta and z. Since z is same as z and that is the third coordinate itself, so we would first concentrate on this change of x and y into r and theta. That means, rather than talking about this 3-dimensional one, we will first talk about the 2-dimensional one, and then we will add up the third one as such. So, if that is says is that is now we would treat u as a function of x and y, and then we want to change the variable from x and y to r and theta using this relationship. So, what the things we do know, that is we will use the chain rule and accordingly we would find it out. So, let us write this r and theta in the terms of x and y. We do know that r would be nothing but square root of x square plus y square, theta is nothing but tan inverse y upon x, and z is equal to z. Since we will be concentrating with x and y, so first we will try to use the derivatives of r and theta with respect to x and y, because both r and theta are just the function of x and y only. So, from here we do get the derivative of r with respect to x. So, now we are writing the partial derivative and we are using this notation rather than using del r by del x, just for the space place we are using this kind of notation where r is subscript x, means it is the derivative of r, partial derivative of r with respect to x. Similarly, if I do have the subscript y, it says is that the partial derivative of r with respect to y and so on. So, if I partially differentiate this one, we do get is that we would get 1 upon 2 square root of x square plus y square downside, that is in the denominator, and the derivative of this with respect to x would be 2x. So, we would be getting is x upon r. Similarly, the partial derivative of r with respect to y, we would get y upon r. Partial derivative of theta with respect to x, the derivative of tan inverse x, we do know 1 upon 1 plus x square. So, using that one we do get it as 1 upon 1 plus y upon x whole square. Then the derivative of y by x with respect to x would be minus y upon x square. So, we just get it simplified it, we get it as minus y upon r. Similarly, the derivative of theta with respect to y would be x by r. Now, we move to the second derivatives, that is r x x. This is saying is del 2 r over del x 2. Differentiating it again with respect to x. So, what we would get 1 upon r, then we would be getting is x times the derivative of 1 upon r, that is minus 1 upon r square into the derivative of r with respect to x is x upon r. So, we would be getting is 1 upon r minus x square upon r cube. Similarly, the second derivative with respect to y, that is differentiating r y with respect to y once more, we will get in the similar manner as 1 upon r minus y square upon r cube. Then differentiating theta x with respect to x once more, y is constant with respect to x, 1 upon r, its derivative is x by r square, x square by r cube. So, we would x by r square. So, we would get theta x as 2 x y upon r to the power 4. In similar manner, theta y is equal to minus 2 x y upon r to the power 4. So, now we will find out the derivatives with respect to x and y and z, change it to the derivative with respect to r and theta using the chain rule. We do know that u x can be written as u r into r x plus u theta into theta x. Now, again differentiated with respect to x, we can write u x x as u r r x differentiated with respect to x plus u theta x, u theta theta x differentiated with respect to x. So, the subscript I am using for the derivative, rather than writing as del by del x, I am using this subscript x. So, now if I differentiate this, this is the product of two functions, one is the del u over del r, another is del r over del x. So, we do get it this one as the derivative of u r with respect to x into r x plus u r into the derivative of r x with respect to x, that is the second derivative of r with respect to x, r x x. In a similar manner, u theta, the derivative of this with respect to x times theta x plus u theta times theta x x. Now, for u r, differentiating it with respect to x, we do again use the chain rule. What we would get, the derivative of u r with respect to r, that is the second derivative of u with respect to r, u r r into r x plus u r theta into theta x. This r x is as such, this term is as such, u r times r x x. Then the derivative of u theta with respect to x, again use the chain rule over here. The derivative with respect to r of u theta, that we would say is del to u over del r del theta. So, u r theta times r x plus u theta theta times theta x, that is the second derivative of u with respect to theta into theta x, and then this term u theta plus theta x x is as such. Similarly, we could get the u y also as using the chain rule, u r times r y plus u theta times theta y, again differentiated with respect to y in the similar manner. We could write u r r y time derivative with respect to y and the derivative of u theta and theta y with respect to y. Again use the multiplication rule of the differentiation, we do get it, the derivative of u r with respect to y into r y plus u r times the derivative of r y with respect to y, that is r y y. The similar manner, the derivative of u theta with respect to y times theta y plus u theta times theta y y. Again use this chain rule using the derivative of u r with respect to y, we do get it as u r r r y plus u r theta theta y into r y plus this term as such u r r y y, and for this again using the chain rule, u r theta r y plus u theta 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 y times theta y and this term u theta theta y y as such. So, now we substitute this r theta r x r y theta x theta y in this one what we had obtained. We had obtained this r x r y theta x and theta y. Moreover, we had also obtained r x x r y y theta x x and theta y y. So, let us first find out u x x. This u x x just now we had obtained as this formulation, u r r r x plus u r theta theta x times r x plus u r r x x plus u r theta r x plus u theta 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 x times theta x plus u theta theta x x. Now, substitute all these. Here what we would get is r x is x by r. So, I would be getting is the coefficient of u r r is r x square, that is x square upon r square. So, we would get x square upon r square times u r r, coefficient of u r theta. We have used one thing, that is the partial derivatives, that function is continuous in such a manner that whether we take the derivative u r theta or u theta r, they are same. So, the coefficient of u r theta is theta x r x here, and from here it is r x theta x, r x is x by r and theta x is minus y by r. So, we would be getting is minus x y upon r square, and we would be getting it 2 times. So, we are getting it minus 2 x y upon r square u r theta plus y square upon r to the power 4 u theta theta plus 1 by r minus x square upon r cube times u r, that is u r r x x, and then u theta theta x x, theta x x is 2 x y upon r to the power 4 u theta. Similarly, we can get u y y, again substituting this r y is y upon r, multiplication of this we would be getting is y square upon r square u r r and then the coefficient of u r theta is theta y r y and theta y r y. From here theta y and r y we would be getting is again x y upon r cube, that is u r theta twice we had with the plus sign now, and the coefficient of u theta theta here would be x square upon r square, that is we are getting is theta y whole square, and then u r as coefficient of u r as 1 upon r minus y square upon r cube minus the coefficient of u theta is minus 2 x y upon r 4, that is theta y y is minus 2 x y upon r 4. So, now u x x plus u y y, what we would get from here, we would get x square plus r square plus y square upon r square, and if you remember r was nothing but square root of x square plus y square. So, x square plus y square upon r square, that is 1. Similarly, this term would get it cancel it out. Here what we would be getting x square plus y square is r square, so 1 upon r square, and this term we would be getting is 1 upon r 1 upon r 2 upon r, and then with the minus sign x square plus y square upon r cube. Again what we would be getting is x square plus y square is r square, so again we would be getting is 1 upon r, and this term will get it cancel it out. So, finally, we would get u r r plus 1 upon r square u theta theta plus 1 upon r u r. Now, so what will be our Laplace equation in the cylindrical coordinate? Laplace equation is this one. We had changed only using this x and y, since z was totally independent, is the same as the third coordinate over here. So, we would use simply u z z for this one. So, what we would be getting is the change coordinates for x and y we have changed to r and theta. We do get it u r r plus 1 upon r square u theta theta plus 1 upon r u r plus u z z is equal to 0. So, this is our Laplace equation in cylindrical coordinates. We will learn about how to solve these equations, but before that we will move to the another coordinates, that is if my surface is having spherical symmetry, that is we will change the Laplace equation in spherical coordinates. What are these spherical coordinates? We do have this as the Laplace equation, this we have to change into the spherical coordinates. Now, what are the spherical coordinates? If you do remember, sphere means is we are having all the round. In the cylinder we were having is one dimension was exactly same as the Cartesian one, but here we are having is all the round. So, we would take about this coordinates in the all the round shape. So, what we are having is in Cartesian coordinates, this point would be simply called as x y z, where we are having is that the distance z from of this point from the origin in the parallel to the z axis, parallel to the x axis and parallel to y axis, that is what we are calling x y z. Now, see, because it is a sphere, so what we do say is we join the origin is being joined to this point. So, now this do not take it as this is not in the x y plane, this is now in the 3 dimensional one. So, origin is being joined to this one, this is what we are saying is the distance between the origin and this point, that we are calling r. So, this is r, then this distance, that this line which is joining the origin to this one, this is making one angle phi with respect to the z axis, that is what we are calling phi. And as usual, if phi make its perpendicular drop on the x y plane, I would get this point. For this point in the polar coordinates, we do have that this distance we were calling r and this angle we were calling theta. So, now r I am not taking, r we are taking is the total distance of this point from the in the 3 dimensional space from the origin, and theta is that angle which it would make if I drop a perpendicular, that is if I take its image in the x y plane, then this angle with this line would be making, that is the line joining the origin to this point in the x y plane, this line what the angle it is making, this is called the theta. Because why we are taking it one? Since we are talking about the sphere, its cross section would be any circle, whatever be the polar coordinates for a circular one, we do have r and theta, but that r we are leaving because that r we could find it out using this r, that is in the is 3-dimensional distance from origin to the point on the surface of the sphere. So, if I just make it out, we do know that from this point if we are talking about, then x is the distance from here to here. So, first let us try to make, that is what we would be getting it in the terms of this r and phi. So, we would get it as r, this distance would be r cos phi, this would be r sin phi, because phi is the angle on this side with the z axis. So, this distance would be r sin phi and this distance would be r cos phi. So, we have got that z is r cos phi, it is all right. Now, what would be x and y? X and y, now we are getting is this distance, that is what I said, is that is I do not require this distance, because this distance is nothing but r sin phi. If this is r sin phi and this is the angle theta, we do know if this let us call this distance as rho, then we do know that x is rho cos theta and y is rho sin theta. Now, what is rho over here? Rho is r sin phi. So, we have got x as r cos theta sin phi, or rather you could say is, now my this rho is r cos r sin phi multiplied with cos theta, but I have written in this manner because we are writing it r theta phi. So, r cos theta sin phi, y is r sin theta sin phi and z is r cos phi. Now, again if we have to change it to this new coordinates, that is in the new variables r theta and phi, we would use this relationship. So, again we would require to change it to in the r theta and phi. So, we require those relations. So, let us see, r would be now square root of x square plus y square plus z square, the distance from origin to this point x y z. Theta as usual would be tan inverse y upon x. Phi is now the angle from here, or you could find it out, that is we do get it x square plus y square would be r square, square root of x square plus y square would be r sin phi and z is r cos phi. So, we would get phi as tan inverse of square root of x square plus y square upon z. Find out the derivative of r theta and phi with respect to x, y and z and the second derivatives that we would be requiring. So, first the derivative of r with respect to x, y and z. If I differentiate it as in the first manner we had seen, here also we would get it as x by r, ry, that is the derivative with respect to y as y upon r, rz as the derivative with respect to z as z upon r. From here if I just go with the second derivative, again with respect to x, so I will get 1 upon r into x times the derivative of 1 upon r, that is minus 1 upon r square, and the derivative of r with respect to x is x by r. So, again we would get 1 by r minus x square upon r cube. Similarly, the second derivative of r with respect to y is 1 upon r minus y square upon r cube, and the third derivative the second derivative with respect to z, that is r z z would be 1 upon r minus z square upon r cube. Now, since this r is this one, now let us come to the derivative of theta with respect to x, y and z. Now, we see is that theta is a function of y and x only. So, its derivative with respect to z would be 0. So, theta x, that is the derivative of x with respect to theta with respect to x, as in the previous one we had obtained. There we had written it r square, but now this r is having x square plus y square plus z square, we would get minus y upon x square plus y square, theta y as x upon x square plus y square, and since it is not containing any term of z, we will get theta z is equal to 0. So, the second derivatives theta x x, we would get it as 2xy upon x square plus y square whole square, because its derivative would be minus 1 upon x square plus y square, and the derivative of this would be 2x. So, we would be getting like this one. Similarly, for theta y we would be getting it minus 2xy upon x square plus y square whole square, and the second derivative with respect to z, again it would be 0. Now, come to this phi, its derivative with respect to x, tan inverse x does has the derivative as 1 upon x square 1 upon 1 plus x square, and then this is a function of x, y and z that we will differentiate. So, using chain rule, u x can be written as u r r x plus u theta theta x plus u phi phi x. Now, what you are seeing is that is I have extended that chain rule to the 3 variables now. The variables are x, that is u is a function of x, y and z, and we are changing this x to function of r, theta and phi. So, we have to apply this 3 way this rule. Again, if I have to find out the second derivative with respect to x. Using similar manner, we could write it out, that is the derivative of u r r x with respect to x, u theta theta x with respect to x and u phi phi x with respect to x. Using the product rule, we could write it as the derivative of u r with respect to x into r x plus u r r x x plus u theta derivative with respect to x into theta x, and then u theta the derivative of theta x with respect to x, that is theta x x. Similarly, the derivative of u phi with respect to x multiplied with phi x, and then u phi the derivative of phi x with respect to x, that is phi x x. Again, for finding out the derivative of u r with respect to x, again we will use the chain rule, and that says is we would be getting is the derivative of u r with respect to r, that is u r r r x plus u r theta theta x plus u r phi phi x. Now, you see is again I am using is that is the derivatives order of the differentiation can be interchanged. Then this term u r r x x has been as such. Then using the chain rule again for the derivative of u theta with respect to x, we get it u r theta r x plus u theta 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 x plus u theta phi phi x times theta x, and this u theta theta x x is as such. Then using the chain rule again for u phi, the derivative of u phi with respect to x, we get u r phi r x plus u theta phi theta x plus u phi 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 x times phi x plus u phi phi x x. So, this is what we have got u x x. In the similar manner, we can use the chain rule. So, u x x we could now substitute the values of that r x and r x x, all those things. So, we do get is now you can see it in your calculations with yourself. You would be getting is as x square upon r square u r r minus 2 x y upon r times x square y square u r theta plus 2 x square upon r cube square root of x square plus y square u r phi minus 2 x y z upon r square x square plus y square to the power 3 by 2 u theta phi plus y square upon x square plus y square whole square times u theta theta plus x square y square upon r to the power 4 times x square y square u phi phi plus 1 upon r minus x square upon r cube times u r plus 2 x y upon x square plus y square whole square times u theta. And then we would be getting is that phi x x times u phi. So, y square z upon r cube upon times x square plus y square to the power 3 by 2 minus 2 x square z upon r to the power 4 times the square root of x square plus y square times u phi. All these we had already calculated. So, we had substituted. So, finally, u x x we have got this long expression. Similarly, we can get using the chain rule u y as u r r y u theta theta y u phi phi y, and then second derivative again using the similarly, that is first using the sum rule, then using the multiplication rule u r y r y u r r y y and so on. We could get it in the similar manner. Again using the chain rule for u r, the derivative of u r with respect to y, derivative of u theta with respect to y and derivative of u y with respect to phi with respect to y, we would again use the chain rule, and we do get finally it as u r r r y plus u r theta theta y plus u r phi phi y times r y, and then u r times r y y as such. Similarly, for this u theta we could write the derivative of u theta with respect to y, u r theta r y plus u theta 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 y plus u theta phi phi y times theta y plus u theta theta y y as such. Then again using the chain rule for the derivative of u phi with respect to y, u r phi r y plus u theta phi plus u phi theta phi y into phi y and u phi y as such. Again you are seeing is we are using is that the order of differentiation is not making a difference in our calculations. Now again we had already calculated what is the coefficient of u r r. From here we would get r y whole square, coefficient of u r theta we would be getting it from here theta y r y, and from here again r y theta y. So, we would get 2 times r y theta y. Similarly, for u r phi r y phi y, and from here again r y phi y, that is 2 times r y phi y. Similarly, we can get for u phi theta from here and u phi theta from here, theta phi from here as phi y theta y, and the coefficient of u theta would be theta y times theta y, that is theta y whole square. Coefficient of u phi would be phi y whole square, and then we would be having this that coefficient of u r as the r y, coefficient of u theta as theta y, and coefficient of u phi as phi y. So, now substituting all these, knowing all this, because we had already calculated r x r y, r y y, theta y and so on, we do get it finally as y square upon r square u r r plus 2 x y upon r times x square plus y square u r theta plus 2 y square z upon r cube times square root of x square plus y square u r phi plus 2 x y z upon r square times x square plus y square to the power 3 by 2 u theta phi plus x square upon x square plus y square whole square u theta plus y square z square upon r to the power 4 times x square plus y square into u phi, and then the terms u r, u theta and u phi, 1 upon r minus y square upon r cube times u r minus 2 x y upon x square plus y square whole square times u theta, and x square upon z upon x square into z upon r cube times x square plus y square to the power 3 by 2 minus 2 y square z upon r to the power 4 square root of x square plus y square times u phi. Similarly, for z u z, again we use the same kind of chain rule u r r z u theta z u phi z. The second derivative again first using this sum rule, that is differentiation of the sum is same as the sum of the differentiations, and then using the product rule for the differentiation, as that is the derivative of the first function into the second function plus the first function into the derivative of the second function, like that. Again using in this the derivative of u r with respect to z or u theta with respect to z and u phi with respect to z, again using the chain rule for this, we would get it finally as u r r r z plus u r theta z plus u r phi z times r z plus u r r z, and then the chain rule over here would give me u r theta r z plus u theta z plus u theta phi z times theta z into plus u theta z, and the third one with the phi u r phi r z plus u theta theta z plus u phi z into phi z plus u phi z. Now, you see we have got that is our theta was a function of x and y only. It was not having any, it is not a function of z. So, theta z, the derivative of theta with respect to z and the second derivative of theta with respect to z, they are 0. That is, this middle term goes out, this is simply 0, and here also this term we would get is this term would go to 0, this term will also go to 0. So, finally, we would be getting is u r r r z, again this term will also go to 0. So, finally, we would be getting is u r r r z plus u r phi z r z plus u r r z, and then this third term u r phi r z and u phi z times phi z and u phi z, this term will also go out. So, now the coefficient of u r r is nothing but r z whole square, coefficient of u r theta from here is sorry, this theta z is not the point, this is 0. The coefficient of u r phi from here is phi z r z, and coefficient of u r phi is here from here is also r z phi z, and then the coefficient of u phi phi is phi z square and u r coefficient is r z z, u phi coefficient is phi z z. Substitute it, we do finally get z square upon r square times u r r minus 2 z x square plus square root of x square plus y square upon r cube times u r phi plus x square plus y square upon r to the power 4 times u phi phi, all the second order derivatives, and then u r and u phi, the coefficient of that is r y your phi y y. So, r z z and phi z z. So, that is 1 upon r minus z square upon r cube u r plus 2 z square root of x square plus y square upon r to the power 4 times phi y. So, now we have got u x x, u y y and u z z in all these terms. You see is that is the coefficient of u r r in u x x was x square upon r square, in u y y was y square upon r square, and in u z z it is z square upon r square. So, if I add up u x x plus u y y plus u z z, I would be getting is x square plus y square plus z square divided by r square, that is same as 1. Similarly, we just see is that is all those terms you can spread on one sheet, and then you can see that some of them are cancelling it out, some of them are being simplified, and finally, what we would get the Laplace equation in spherical coordinates as u r r plus 1 upon r square sin square phi u theta theta plus 1 upon r square u phi phi plus 2 upon r u r plus cot phi upon r square u phi. You see we are having here certain terms in the terms of x, y and z. What we will do finally is that is square root of x square plus y square, or that is x square plus y square, that is nothing but r square sin square phi. So, like that we would be getting, and similarly tan phi is your z square root of x square plus y square upon z. So, like that we would be substituting this in those terms, we would get it this simplified form, this one. Sometimes it is easy to write this differential equation in another manner also, that is much easy for solving the equation. What is that alternative form? This is my equation, Laplace equation in spherical coordinate. We have got u r r plus 1 upon r square sin square phi u theta theta plus 1 upon r square u phi phi plus 2 upon r u r plus cot phi upon r square u phi is equal to 0. Now, you see here I am having one term of u r r, and here I am having is one term of 2 upon r u r, and we are having is 1 upon r square all the times in the downwards, except at this point and this point. So, first we will take 1 upon r square outside. If I am taking 1 upon r square outside, here I would get r square times u r r, and then here I would get 2 times r times u r. So, we could simply write it out in that manner, u r r plus 2 r u r, that is this term I have written first. Then from here 1 upon r square has gone, it would be 1 upon sin square phi, and 1 upon r square has gone from here also. Cot phi means we could write it as cos phi upon sin phi. So, again 1 upon sin phi from these two terms I would take it out. If I am taking out this, this should be 1 upon sin square phi. Well, so, we would be getting it as sin phi u phi phi plus cos phi u phi plus 1 upon sin square phi u theta theta, that is this term is as such. So, from here what we are getting is 1 upon r square is outside, 1 upon sin phi I have taken out. So, u phi phi the coefficient I have to multiply sin phi, and then I would get cos phi u phi, and this 1 upon r square sin square phi times u theta theta, that is as such. This is equal to 0. This would be my equation. So, now because it is equated to 0 and r square, this is the distance, this can't be, we are taking a point. So, this is we are not taking it as a 0, some sphere of some radius r. So, the boundary surface we are not taking it, that is any point on the surface that would never give me the distance 0. So, we can take it that side, and we would get it simply the equation like this one, what is in the bracketed one, that is equated to 0. So, this one, let us take the first two terms. We could say is that is if I take the function r square times del u over del r, u r means del u over del r. If I differentiate it with respect to r using the product rule, I would get it r square times. So, here actually I think is I had forgotten r square. So, r square has to be here. So, r square times u r r, and then the derivative of r square is 2 r and then u r as such. So, this is what you are getting is r square del u over del r. Then 1 upon sin phi. Now, here if I see the function, if I take sin phi u phi, its derivative with respect to phi would be sin phi times u phi phi, and then the derivative of sin phi is cos phi and u phi as such. So, it is del upon del phi of sin phi del u over del phi, and then the third term is as such. So, this alternative form is many times much easy to solve. So, we do also use this alternative form, or rather in our example we would be using this alternative form. So, this is what we have changed our Laplace equation into either cylindrical coordinates or spherical coordinates. Let us try to see is that is how to find out the solution. So, let us first try with the surface or the boundary as sphere or spherical with a spherical symmetry. So, we would use this spherical Laplace equation in spherical coordinates. For this, let us see the boundary value problem here, how we could define. Suppose my region of interest is this ball, that is a sphere, and the boundary is the surface of this sphere. What we have been given, if the function u is independent of theta on this surface, that the boundary condition is given independent of this theta on this surface. So, we want boundary condition on a sphere S of the radius r. Now, this radius also we had fixed. We say is u r theta phi is f of phi, that is independent of theta. That says is if I make this kind of situation is arising in electrostatic potential, where r in the temperature, where this we are talking about that we are taking a ball kind of things, and we are talking about the potential inside this or outside this ball. If I make it independent of theta, what it says is that I would get my differential equation, this Laplacian equation would be, this is governed by this Laplacian equation. So, I have written this Laplacian equation, that what we have written the second form as here. What it would give me, that is u theta and u theta theta would be 0, that is this term will go out, and my solution, if it is independent of theta, u theta theta would be 0. That says is I would get the only two terms, del by del r of r square del u over del r plus 1 upon sin phi del upon del phi sin phi del u over del phi is equal to 0. So, now what we have defined, we have got, that is if I am interested to determine the electrostatic potential on a spherical region, I could use it, and that what we are saying is it is independent of the third coordinate theta. The solution is independent of third coordinate theta. Then my solution would be u r phi, and the governing equation then would be del upon del r, r square del u upon del r plus 1 upon sin phi del upon del phi sin phi del u upon del phi is equal to 0. One more thing we would like to say is that is this potential has to be go to 0 as r approaches to infinity. That is, we say is that on this all those potential, all the inside this, because the boundary condition is on the surface. So, inside the sphere and outside the sphere. So, inside the sphere the boundary condition will come over here, outside the sphere we do say is that is limit as r approaches to infinity u r phi is 0. So, now what we are having is we are being defining our boundary condition on the surface, that is on the boundary S. The function is being described on the boundary S. So, this is a Dirichlet kind of problem, that is the first kind of boundary value problem, that is called the Dirichlet problem. So, let us learn it how to solve the Dirichlet boundary value problem, where my differential equation is this and the boundary condition is this one, using this one more condition on the limiting case. So, we would learn how to solve this boundary value problem, the Dirichlet problem, that we would learn in the next lecture. So, today what we had learned that is, if we have a 3-dimensional Laplace equation, this is one important application partial differential equation is which is arising in basically electrostatics are in fluid flow and heat flow kind of things. What we had learned is that is when we are talking about heat flow and fluid flow, it is a 2-dimensional Laplace equation which we had learned little earlier. Now, we are talking about the electrostatic, that is potential, and we had learned that is solution, which we are discussing, that is how to find out the solution. This theory we are calling that is potential theory. So, today we had made one kind of change. If my surface is spherically symmetric, or if I am changing my coordinates, Cartesian coordinates to spherical coordinates, then I would go ahead with the I am changing the Laplace equation into spherical coordinates, defining the boundary value problems, that is Dirichlet problem, the first kind of boundary value problem. So, next class we would, or next lecture we would learn how to solve this Dirichlet problem. Thank you.